Hello and welcome back to Scrap Paper and Philosophy. And last time you might have come to the conclusion that I was completely stoned because I said something about a sanity check and then I applied the wrong sanity check, which means that I guess I'm insane. And but let's do the right sanity check this time. So we were arguing that because E equals mc squared, that this mass is traveling at the speed of light, or what we think of as the speed of light. But what we should have been thinking is that no, kinetic energy is not equal to mv squared. Kinetic energy is equal to 1/2 mv squared. So no, velocity does not equal to the speed of light, case closed. And at this point, well, I can tell you I have actually other reasons for believing what I do. And they have to do with the fact that we use electromagnetic means to record reality exactly. Sensory perceptions of reality exactly. And we use electromagnetic means automatically, which is different than a painter doing a portrait, because the painter is actively involved in the process, right? He's changing the reality, so to speak, and we see that. I mean, if we take a picture with a camera instead of doing a painting, just the fact that the painting takes hours and hours, and so there'd be no way that the painter could automatically, take a snapshot. A snapshot is a very it's a machine, right? We have a machine to do it. So why can we have a machine to do this? And anyway, let me backtrack and discuss this formula for a moment. So we have kinetic energy equals to 1/2 mv squared, right? And that's coming from momentum. That's my best guess. It's coming from momentum, because momentum equals mass times velocity. And if we do the integral of momentum with respect to velocity, we get 1/2 mv squared, right? Because the derivative of 1/2 mv squared is going to be mv. But of course, we don't like indefinite integrals, so we rather think of this as the integral dv v equals 0 to v1 or v0, whatever. So that is going to be equals to 1/2 mv squared from 0 to whatever velocity we got, let's say v1, and that's going to be equal to 1/2 m v1 squared minus 1/2 m, well, instead of babbling, I can just do it. We all know what it turns out to, right? It's 1/2 m v1 squared. So we have a velocity v1 of a mass m. We want to know its kinetic energy. We say that this is the kinetic energy. And the reason for saying this is that the kinetic energy is an integration operation. And the integration operation is on all possible momentums that the particle can take, from a velocity starting at 0 all the way to the velocity v0. You see, we could also integrate from, let's say, well, no, we couldn't. You see, this has to be 0 in order for this formula to be 1/2 mv1 squared. So that's interesting. And we'll have to talk about that later. But before we even do so, let's talk a little bit about momentum and about the law of conservation of momentum, because that's more fundamental for what we're going to need eventually. And of course, like I said, I haven't convinced myself that... Well, actually, I thought out the ideas I have to say here. I thought about them when I wasn't stoned, so I can't use the argument that I'm stoned to kind of like weasel my way out of saying that I'm all wrong. I'm just wrong because I'm stoned. I'm not really wrong because I'm stupid. So no, that's not the case here. So, let's go through the whole gory exercise of deriving the law of, the law of conservation of mass first, right? So we have like a bunch of particles in empty space, maybe something like this, and they're traveling in all sorts of directions, and so there's no conservation of mass in the system. However, if this is a vacuum, it's all empty space. We should really call this the law of the empty space. If this container is big enough, there's conservation of mass. And that being the case, we can take this container to be the mass of the entire universe. And the entire universe is contained by a vacuum of empty space. I mean, it's there's a vacuum extension here. You see, I'm trying to think like Newton, right? I'm not trying to think like a Big Bang theorist. So here we have a velocity. Okay, we have a velocity that's going to be 0, and because the container, we don't have to expand it, right? If there was leakage, you see, if some of these particles started leaking, then we would have to expand the container for the physics to continue to work. And, what physics am I talking about? Well, I'm talking about the physics of a block of mass, a mass m, and the mass is, it has empty space, and it's traveling at a velocity v. And because the space is empty, there's no friction, and because of the absence of friction, mv doesn't change. So the change in mv equals 0. And that's really a statement about the conservation of mass, because the mass isn't changing. That's also a statement about the conservation of velocity, because there's no forces acting on the mass. Right, so there we have it. Because m doesn't change and v doesn't change, the derivative of momentum with respect to time, right? Is it Well, I don't remember. I think Newton in Principia, he worked this thing out with momentum, and he had that the sum of the momentums of the entire universe equals zero, or something like that, and we can see why. Okay, so let's get a little bit more into this. If we have, let's imagine mass is just like kind of like a blob, and that blob is traveling in empty space, right? And that blob hits a barrier, and we think of the barrier as a force that's going to act on the mass, because the way we know that force is acting on the mass is that the mass is going to deform. This blob, as it hits the barrier, actually both the barrier and the mass are going to deform, right? So the barrier is going to go something like this, and then I don't know, and then the mass is going to go like this, and then there's going to be all sorts of elongations and deformations, and then the mass is going to bounce back, and the barrier is going to be like vibrating back and forth for a moment, but when it eventually settles, maybe there was no permanent damage, and the mass just reflected and bounced back. And both of these elements are affected, right? Both the mass and the barrier are being affected by this collision, and so that's why we have to view both separately. And then when we do the sum, the momentum never changes. The momentum always stays the same for the entire universe. And I'll try to do a more let's see. Maybe I should go back to the quantum mechanics, because that way I'll actually discuss something that I'll actually discuss something that I already showed you before, and I haven't discussed it. And this is about distance, time, matter, and energy. And as soon as we have distance, time, matter, and energy, these four quantities, we can expand distance into the coordinates x, y, z of space. And there's time, and there's matter and energy. So we still have this. So now we have six quantities, right? We have a sextuple, and if we think about what quantum mechanics, or I should say physicists, tell us about quantum mechanics, is that one thing we can do, I mean, at least theoretically, is to order the entire universe with this sextuple, x, y, z, t, the real part of the wave function, which is this thing right here, and the imaginary part of the wave function, which is this thing right here. So we still have essentially four quantities if we think of x, y, z as distance, right? And this is why I only had like 4 dimensions here. So now here we have 6 dimensions. And but one thing that's very interesting is that there's this coordinate system is a complete fiction in a sense, because x, y, z coordinates, they don't exist. What really exists is a distance, right? And between two objects. And we can think of the distance from the origin as the square root of x squared plus y squared plus z squared. But what we would really want is a distance between two objects, right? And any real physics will have to take that into account. And the way this ends up happening is, expressions like, the sum of squares end up showing up in the what's it called, equation, the unpronounceable equation, whatever, that equation from quantum mechanics. So we have that, and we have that we have that equation solving the entire hydrogen atom, right? Taking the origin as the center of the hydrogen atom. Well, you know, um, the point I'm really trying to make here is that physicists tell us that this is how we order the universe. We have this sextuple ordering the entire universe, but we can't be sure because in engineering classes they don't really give us tools to work with this expression into physical results, right? Into measurable results. That's the word I'm looking for. So this video is turning out to be longer than I should do this. So maybe I'll leave this for like another time. And once again, thanks for watching. See you later.